Hello, my name is Valentin Voroshilov. I've been teaching physics at different places, mostly at Bridgewater State and at Boston University. And I've been doing this for a long time, and I consider myself to be good at doing that. Unfortunately, I can't present this lecture face-to-face to you. That's why I make this video. However, I'll see you soon next week on Tuesday, according to our general schedule. So our materials will be available on Blackboard. The syllabus, homework assignments, the lecture notes, all materials will be there. So please check if you have the access. And if you don't have the access to Blackboard, please let me know. And our textbook is free for download from this link. And a copy of a textbook should be available through Blackboard. Maybe not the latest copy. They make slight modifications every year, but they're all the same, basically. So if you check the syllabus, and you can see our schedule, what topic will we talk about, and what labs. The lab schedule might change a little because Professor Hernandez is responsible for running labs, but he will tell me if any change happens, and I will inform you, or he will inform you directly. And the syllabus also tells you in general how the final grade will be calculated. It's based on your lab grade, homework grade, and participation grade. And for participation grade, all you have to be is just be here and participate. And the lab grade is calculated by Professor Hernandez. And the homework grade is based on the homework. The homework 1 is already available on Blackboard. You should print it out and bring it back to me when it says due to. And this is a generic Bridgewater State grading scale. Usually I don't make any changes unless something really drastic happens with the distribution. And in the end, we can calculate the total grade using this equation. It's based on 2 midterm exams, final exam, lab grade, and homework and participation. There's a common misconception, I would say, a myth, that physics is really hard. I don't think physics is hard. First of all, there are much harder things in life than physics. For example, learning how to balance on a rope is much harder for many people than learning how to solve a problem about person balanced on the rope and calculating all the forces. We will do something like that later. So physics is not really hard if you follow the logic. Physics has logic. Physics is applied mathematics. We have to use some mathematics, but we don't have to use any calculus. Simple algebra and the trigonometry is sufficient. And we study physics because we want to use the knowledge to make our life better. Eventually, we have to use our knowledge to make reliable predictions. And if we can make reliable predictions, we can build things which are convenient for us, like a projector, a car, or airplane. Every science has a mission of making reliable predictions. That's it. That's what science is for. That's what science is about. And when we look around to make a prediction, we search for things which repeat themselves. We call them patterns. If we observe a pattern, that pattern tells us how to make a prediction. For example, every morning we observe the sun rising and then coming down. So we observe it again and again, and we can make a prediction. It's going to happen tomorrow, the day after tomorrow, the day after tomorrow, etc., etc. And there are many different patterns in nature. Yeah. Procedural patterns, visual patterns, logical patterns, and audio patterns, social patterns. Of course, for us, most important patterns are numerical. Like this is a famous Fibonacci sequence, 1, 1, 2, 3, 5, and we can see the pattern. If we see the pattern, we can predict what should be the next number in this sequence. And we don't really think about it. We just know it. We know that to find the next number, we have to add 2 previous numbers, because that's what our brain tells us. 1 plus 1, 2, 1 plus 2, 3, 2 plus 3, 5, 3 plus 5, 8, etc., etc., 13 plus 21, 34, etc., etc. And our brain is a very powerful pattern recognition machine. If it wasn't be for our brain, we wouldn't be able to do science. In physics, we have special patterns. Some we call definitions. Yeah. We define this to be equal to that. Like the easiest definition is speed. Speed is distance divided by time. Well, technically, it's average speed. And a definition depends on common agreement between people. Someone offers a definition, and if it works for everybody, everybody agrees eventually to use it. Laws don't depend on agreement. We study nature, we search for pattern, and that pattern eventually is described mathematically in the form of some equation, and that equation is a law. And of course, we use some mathematical procedure, not really physical laws, but handy part of knowledge, equations, functions, graphs. When we study any phenomenon, we start from observations. So this is a standard free fall situation. I release a ball from rest, and it falls. We do it again and again and again until our brain sees the pattern. And the pattern is, if we take a cell phone or a camera and tape the motion of this object and then look at it every second or every half of a second, we can see that distance changes in a certain way. We can take a ruler and measure distance as a function of time. We can put those numbers in a table. Then we can graph how position changes in time. And eventually, we can derive an equation which represents this relationship. And if we have that equation, now we can make a reliable prediction. We can ask, for example, what would be y number equal to when time equals, I don't know, 0.736. So all we have to do is plug in time, take a calculator, and calculate. And speaking about the calculator, any calculator with the standard trig functions will do. So this is a summary. Physics is a science, and every science is based on a vast amount of data. We have to analyze those data, arrange them. Not everything which is called science is actually a science. For example, physics is science. Teaching physics is not. There isn't reliable data which would help us to make a prediction, for example, who's going to get a certain grade in the end. It's just impossible. So when we observe things in physics, when we see something important, we give it a name. Like, that's what we call a distance, that's what we call time, that's what we call speed. Mathematical definition usually helps us to relate some of those names. We call them also variables, the physical quantities. And in order to assign a number to any of those physical quantities, we have to use a specific procedure. That procedure has a name, a measurement. If you Google measurement, you can see something like this. There is a science called metrology. That's what they call measurement in metrology. It's not very good for us. It's not very specific for physicists because it doesn't specify a procedure. In physics, this is what we call a measurement. If we want to measure certain quantity, first, we have to set a standard of that quantity. Second, we have to set a procedure which would allow us to compare all other objects which have the same quantity with the standard. And in physics, we have several important standards. Number one is time. To measure time, first of all, we need a periodic motion, something like this, a motion which repeats itself. 1 Mississippi, 2 Mississippi. So now we can call this time interval 1 second, for example. And now we can count how much time, how much seconds, how much motions like this is fit in any time interval. Of course, we don't do it anymore. Well, we can use a kitchen timer or a clock to measure time much more accurately than using this ball and a string. And if we use a special set of measurements, we call them units, physicists and engineers and scientists in the whole world agreed on using the same set of units, the same set of standards. So there is a special system called International System of Units, or SI. So if we measure time using the International System of Units, we have to use seconds. But of course, in everyday life, we also can use minutes, hours, days, months, years. It's up to us. But when calculating anything related to time, we have to use seconds. Second standard is the standard of length. And the standard of length has been changing historically. The easiest and the most common standard is just a rod chosen to be equal to 1. 1 what? Well, the rod like that was called 1 meter. It was divided into smaller parts, decimeters, centimeters. And if now we want to measure the length of something, we just have to count how many of these standards can we fit. For example, if I want to measure the length of this bench, I just have to count 1, 2, 3. I fit it 3 times exactly, so the length of this bench is exactly 3 meters. And the next standard is the standard of mass. So to measure mass, we could use our own feelings, right? Okay, well, probably, yeah, I feel like it's maybe 1 kilogram. But we people are not very good at accurately measuring things. So that's why we have invented scales, a spring scale or an electronic scale, which is a graduated device. So I place a standard which I call 1 kilogram. I write number 1, and then I can calibrate. It's smaller parts, 10th, 100th grams, milligrams. And now any other physical quantity can be described in terms of seconds, meters, or kilograms. And now let's go to the second part of this video, Physics 2. So, as you know by now, my name is Valentin Voroshelov, and students call me Mr. V. And today we start a topic about pressure density. Eventually, we talk about static fluid. First, let's give a formal definition of pressure. And a pressure is equal to a force acting on certain surface divided by the area of that surface. For example, if this surface is 1 meter squared and I push in with 10 newtons, the pressure would be 10 newtons over 1, 10 what? Well, a newton over a meter squared. That unit has a name pascals. And if we use international system of units, we should use pascals to measure pressure, not pounds per inch squared or something else. And let's calculate as an example of a pressure from a cylinder on a table. So this cylinder has a given mass, 8 kilograms, and its base actually is rectangular. So it has sides 8 centimeters by 12 centimeters. So if you want to calculate that pressure, all we have to do is just apply a definition. Force over area. And the force is not equal to the mass. The force equal to the force of gravity acting from the cylinder on the tabletop. And if the mass is 8 kilograms, G is about 10, the force is about 80 newtons. And if we look from above, we can see the base 12 centimeters, 8 centimeters. We need to calculate the area. But in order to use the right unit, we have to use meters, not centimeters. So 12 centimeters is 0.12 of a meter, 8 centimeters, 0.08. And that gives area. To make sure everything is correct, 0.12 times 0.08, 0.0096 meters squared. Now we can finish our calculation. Force over area, 80 newtons divided by 0.0096 equals 8333.3. That's a newton over a meter squared, or we could say pascals. This is not actually a large number. For the pressure, atmospheric pressure is even higher. We'll talk about it later. Now, if we would have a class, I would ask you to answer this question using a clicker. We get the same box, and we change the way we place it on a tabletop. How should that affect the pressure? Well, first of all, if it's the same box, that means before and after we changed the orientation, we did change the mass. The mass remains the same. However, what do? We change the area. The area is different, and this area actually is greater than the initial area. The pressure depends on both variables. If the mass is constant, in this situation, the force acting on the tabletop is also constant, but the area changes. How? The area increases. If area goes up, and that's a numerator. Numerator remains constant. The denominator increases. That means the pressure should go down. So the right answer is P1 is greater than P2. I want to show a simple experiment which demonstrates the importance of pressure. This weight is about 500 grams, and this rod is even lighter, for 50. But if I place them on a surface of, well, salt, we can see the difference. So this weight released, it doesn't go any deep. No, stays on the surface. But if I take this rod, I let it go, it gets deep. It gets about an inch deeper. They have the same mass. That means they exert the same force, but force distribution across the surface is different. And that makes the difference. Using this wide surface is like using snowshoes for walking on snow. Now we need to talk about another physical quantity which describes a material any object is made of: density. According to the definition, the density, or we should say average density, is equal to the mass of an object divided by its volume. And here we can see examples for the density of air or water, iron, mercury. The unit of density is the unit of mass divided by the unit of volume. If we use international system of units, that's a kilogram over a cubic meter. And we have no special name for this unit. We just call it a kilogram per cubic meter. Could have been gram per cubic centimeters. Also a common unit of density. And of course, we can always make a transition from one unit to another, and we will later. Now I just want to mention, because, well, we don't like fractions, and the density of all major materials have been measured. This is how usually we use this equation. We know density, we can measure volume, and we can calculate the mass. Well, first let's practice calculating density. This is our cylinder, and we know that the mass of the cylinder is 8 kilograms, and now we know all the dimensions. So if you want to calculate the density, we have to divide the two numbers, mass and volume. That's 8 kilograms, and now we need the volume. So if our cylinder, actually we should say a prism, it has dimensions 12 centimeters by 8 centimeters by 22 centimeters. To calculate the volume, we need to multiply these numbers, and actually again we have to convert centimeters into meters first. 0.12 times 0.08 times 0.22. That gives cubic meters. 0.12 times 0.08 times 0.22 equals. That's a small number. Usually it is always a small number. Cubic meters. It's a tiny portion of a cubic meter. And in physics, people would write it in a scientific form. 2.1 times and 1, 2, 3 decimal points to the -3 cubic meters. So now the density would be equal to 8 over 2 times 10 to the -3. I rounded up, which is about 8 over 2 times 10 to the 3rd. That's what good about scientific notation, which is 4 times 10 to the third kilograms per cubic meter. What does it mean? It means if we had 1 cubic meter of this material, put it on a scale, the mass of that object would have been 4,000 kilograms, 4 tons, 4 metric tons. One more example. This is a classical experiment, and I will show you this experiment soon. But in this situation, we just imagine that we'll have all the equipment we need. We have a scale, we have a graduated cylinder. The scale tells that the weight of rock is 20 newtons. That's weight. Weight, which is equal to mass times G, is 20 newtons. That gives us a way to calculate the mass, 20 over 10 to kilograms. So the mass is 2 kilograms. To get the volume, we see how it changes the reading of a graduated cylinder when we immersed this rock in water. The volume increased by 2 times 100 cubic centimeters. So 1, 2, 3, 4, 5, 6, 2 more readings. So now we know the mass, now we know the volume. We can calculate the density. The density is equal to 2 kilograms divided by 200 cubic centimeters. Well, it's not a good thing having mixed units in one calculation. So what do we have to do? We need to convert cubic centimeters into cubic meters. Well, 1 cubic centimeter is a little cube, 1 centimeter, 1 centimeter, 1 centimeter on each side, and the volume of this cube will be equal to 1 times 1 times 1 cubic centimeter, or in meters, 1 over 100.01. 0.01 times 0.01 times 0.01, 0.121212 cubic meters. But of course, we would need to write it using a scientific notation. Basically, it tells us that if we multiply by 1,000,000, 10 to the 6th, on both sides, 1 cubic meter fits 1,000,000 cubic centimeters. So if I have huge cube, 1 meter by 1 meter by 1 meter, each meter equals 100 centimeters. So inside this cube, we will count 1,000,000 cubic centimeters. That's what it means. Which means 1 cubic centimeter is equal to 1,000,000th, 10 to the negative 6th of a cubic meter. Now we can finish our calculation. 2 over 2 is 1. And here we have 10 to the negative 4 in a denominator, which makes it to the positive 4 in the numerator, a kilogram per cubic meter. So it's something solid. And now let's do one more example related to an experiment. And this is how we can measure average density of a material something is made of. So this something is inside. And first we can measure mass, 441 grams. And now we can measure the volume. We just need to put it in water. Right now the reading is 700. And here it is. Now it's 970. So in our actual experiment, we've measured the mass of that object, 441 grams. And when we placed that object in water, the reading has changed from 700 to 970 watt. Well, those are milliliters. Milliliter. What is a milliliter? 1 milliliter is 1,000th of a liter. That's what milli is. What is a liter? One liter is a volume of a cube which has 10 centimeters, 10 centimeters, 10 centimeters on each side. So, what is the volume of 1 liter? Well, if we want to use meters, we need to multiply 0.1 3 times, which is 10 to the negative third of a cubic meter, which means you multiply by 1,000, 1,000 liters will give a volume equal to 1 cubic meter. So if we have 1 cubic meter, 1 meter, 1 meter, 1 meter, it will fit exactly 1,000 liters in it. How large is 1 liter? Well, 10 centimeters by 10 by 10, something like this. If you have a big soda bottle, it fits 2 liters of soda in it. So 1 milliliter is 10 to the negative third times 10 to the negative third of a cubic meter. So this is basically 1 cubic centimeter. Well, now we can calculate the density. Well, to convert grams into kilograms divided by 1,000. And the difference is 270 milliliters. So let's just calculate it. I have no more rooms left. 0.441. Well, first I want to multiply by million instead of dividing by 1 millionth. Equals, and now divided by 270 equals 1633 a kilogram per cubic meter. Well, that's something solid. Steel, brass.